Good morning. My name is Ben Yu. And as Dr. Tom Nesbitt mentioned, this is a very, personally, a very emotional day for me as well, because I remember December of 1998, when I joined UC Davis. The first people that I want to meet are the ones who are involved in medical area, medicine. So I remember Tom and David coming over to our main campus in UC Davis Medical Center, UC Davis main campus. And with John Heritage, we had a meeting, talked about, wouldn't it be nice to set up really exciting next generation network, look into next generation healthcare, and so on. And there are a lot of things we had to do. And some people said that this day will never come. And it came. I was watching the presidential election debate, and Barack Obama stood up and said, some people said this day will never come. He also said, yes, we can. So it's amazing that we can do this. I'm very excited about this. And also, I would like to thank Ravi Namada because along with this team, we looked into setting up a network. And between Davis campus and Medical Center, we had a lot of activities going on. There are about 25 miles. And back then, we had only 3 T1 lines. We were relying on basically 4.5 megabit per second. And sending MRI data was basically an overnight thing. And you just have to send it out and then just hope that the data will go out overnight. And Ravi Namana, without telling the managers, he went through every manhole in Sacramento, tried to find ways to put the fiber. And now we have 8 strands of fiber between Medical Center and Davis main campus. And I'm going to talk about some of the wonderful things that we can do in the future. I have a lot of collaborators. I have Dr. Zi Ding, who's here, who's a wireless network expert. So what will the next generation healthcare look like? This is kind of my, looking at today towards maybe 5-10 years down the line. We'll probably have a lot of wearable sensors looking at a lot of things. Dr. Pomeroy mentioned that the cell phone may have microscope and so on. Some of these intelligent handheld device will have a lot of functionalities, including microscopy and computation, communications, data processing. And I'm going to argue that in the next generation, the Google data center that handles 100 terabytes of information will be actually in your handheld in about maybe 10 years down the line. And we'll want to communicate between them, and we'll be communicating with a lot of sensors that can be wearable or even implanted in part of your body that looks at vital signs of your heartbeat and blood pressure and so on. There are a lot of other cognitive functions that can be imaged on a functional MRI. And there are a lot of doctors and patients who are studying these things. And then we have wonderful genome studies. And perhaps someday we can do this everything online, look at what's going on in your body, in real time find out how we can solve the problems, or maybe deposit this data, and using genome sequencing and data mining and data processing, maybe someday you can find the solutions to uncurable diseases relatively quickly. At the UC Davis Medical Center, there is really one of the few very wonderful, one of the few in the world, wonderful robotic surgery systems. So if you put everything together, you can think of having world expert doctors sitting at remote places working with the patient and having these images going back and forth and trying to cure the disease of the system or the people and so on. But the thing is that you need a lot of bandwidth. You cannot really tolerate latency. If you have a lot of images that have to be compressed and so on, each compression takes 2-3 seconds to compress, and these latency will not allow doctor to respond right away. Your doctor may be far away. As somebody mentioned, now we're looking at telemedicine going out to Africa and India, and you may have doctors sitting in Europe and America trying to help patients in remote places. So then end-to-end meaning that multiple doctors and the patient going through wireless, optical, wireless network, you need to support high quality of service with high throughput, at the same time low jitter, low latency with high quality of service at the same time. So this is kind of a really challenging issue for the technologists like us working with the real medical doctors. Okay, so just an example. At my home, I just got the HD TV. I got excited, 2,000 by 1,000 type of pixels. But I think the next generation medical healthcare really has to do with three-dimensional. Back in 1998, when I was talking with Tom and David and so on, other people at Medical Science, I was told that the medical doctors, the medical school residents were trained to look into the MRI scan and CAT scans, and kind of like a slice by slice. They may look at like hundreds of these two-dimensional pictures and construct what the three-dimensional brain or three-dimensional image look like, kind of imagine these things. Now the tools are much better, and Oliver and other people, I'm working with Bernd Hamann, and Luzina has done a lot of nice work too, looking at these three-dimensional images, and you can kind of using computer, you can kind of make dissections, and you can look at this in many different perspectives. You can immerse yourself in this type of environment and see what the patient, that maybe this is like a blood pipeline, and see, you can actually even touch and feel type of stuff and see how you can image this thing. You may have multiple doctors working together on a patient's illness and try to find ways to cure the problems. Again, the high definition image like that, and again, also this is a functional, meaning that you may have 30 frames per second that you want to take, and with low latency, right? So you may have 1,000 by 1,000 by 1,000 pixels. That's a 1 billion pixel already, and you have 28 bits of color per pixel, and then you want to have real-time 30 frames per second without compression so that you have no latency. That's already a 1 terabit per second capacity, and at your home, you may be lucky to have about megabit per second DSL network. Here, you're talking about million times bandwidth of that. Now, if you have multiple doctors working together, that then becomes a multiple of terabit per second. Now, I happen to be working on optical network that supports multiple terabit per second. However, it's now a challenge to look into how you can do this with wireless and so on, and then achieve end-to-end high-quality networking and high throughput. So this was kind of the theme that we pushed, believe it or not, 10 years ago when myself starting working with Tom and David and Ravi, and then CITRIS came along. CITRIS came up, and back in 2000, 2001, we were writing these proposals, and the first thing I put together there was we have a dream. We'd like to put CITRIS network across starting with the 4 campuses we work with. So Davis, Berkeley, Santa Cruz, Merced. And Davis was kind of unique because between Davis and Sacramento Medical Center, we had 25 miles of on-fiber distance. There were a lot of exciting things that we could do if we were all connected together. And for instance, not only can you do healthcare with the multiple doctors, but you can also link this with smart classroom, where the state-of-the-art research activities in healthcare are at the same time learned by the new medical doctor to be, the resident doctors and so on. So smart classrooms at multiple campuses, and telemedicine, and visualization at multiple sites, and so on. Also linked with smart building at Berkeley and so on. So this was kind of an exciting dream. And then we pushed this idea quite a bit, and back then there were 4 proposals for CC. CITRIS is one of the 4 California Innovation Science and Institute. we are the only CC that pushed this type of proposal. Cal IT Square at San Diego and Irvine looked at this idea, they liked it. UCOP in Oakland looked at our proposal, they said this is very unique in CC and they like to expand this to all campuses in California. And in fact, that became the idea of part of the Calrun XD. So Calrun XD idea now merged with CITRIS. So CITRISnet will be incorporated on Calrun XD using the fibers now and Davis and so on, that we can support multiple terabit per second of networking in the future. And then this can be part of that telemedicine network, that $22 million project. That's really exciting. All right, so then the next step is to utilize this fixed fiber optical networking, fixed wireline networking, and then make it ubiquitous. So then you need to put the wireless network on there. So then the new networking that's happening right now is called wireless mesh networking, meaning that wireless network is not just the kind of broadcast type of networking, but it's more like the wireless node can work like a router. And you can establish mesh networking. So in the urban area, you can put antennas in the tall buildings and support the metro area. There was supposed to be a talk before me, WiredNet. The speaker is not here, but in WiredNet, people deploy these networks in Africa or India where there's no infrastructure at all. So without the infrastructure, you can set up these tall towers, and because of the power issue, you end up with having the antenna beam form and go directional, and you can have point-to-point networking, just like a wireline network has point-to-point and then router network. Basically, you can deploy these networks relatively inexpensively, relatively easily, and then support reasonable amount of bandwidth with the 802.11 technology that WiredNet is using. Typically, you get about 50 megabit per second. With the beamforming, you can go about 200 kilometers. What we are looking at right now is to use the next generation technologies that are using the unlicensed band to go gigabit per second Ethernet and beyond. So these are using 60 gigahertz or 80 gigahertz type of unlicensed band. Commercial units can go 10 kilometers. We can beamform it better to go to about 200 kilometers. Now, if you put multiple of those things, you can start to put 10 gigabit per second. Beyond that, you can start to use optical wireless and go 10 gigabit per second. And you can even go terabit per second networking with the all optical wireless. And there are commercial units that are available. The next step that are interesting is that using this wireless networking, perhaps we can deploy ambulances, because we know that the first minute of, if the patient falls through heart attack, the first minute is very critical. And the ambulances can maybe barely get to the patient within a few minutes or 10 minutes. The first aid you have to apply to this patient, very, very important. But as I said, you like to have very high quality of service to these patients, like imaging. Not only do you measure the blood pressure and heartbeat, you want to also image your heart functions and other organ functions and send out these images through high capacity wireless without compression. So you can put these high capacity antennas with beamforming on ambulances and deploy this wireless mesh networking on a mobile basis. It's kind of challenging, also new. We received the new CITRIS seed funding project on this, so we're currently looking into this very actively now. So you can actually start applying these wireless mesh networking on ambulances. So this is kind of a wireless mesh network idea. There's a next speaker by Prasant will also talk about the test bed. But you can have wireless mesh network platform. You can have moving mobile client. I'm just going to give you two simple ideas. One is that in wireless mesh networking, you can say you have a routing set up from source to destination, but you can actually have redundant path set up so that you can support resiliency and redundancy to support high quality of service. And Professor Ziding is applying network coding so that even if part of the network is interrupted and so on, you can still recover the data and so on. We can also apply the hierarchical networking idea to put the campus-wide network to regional network and long-distance network as well. So the intelligent network using GPS and beamforming, that'll be exciting. So I just saw a sign that says stop, so I'm going to show just one slide and then end my talk. Basically, one last thing that I want to talk about is that the amount of data that we are handling is doubling every year. Especially in the medicine area, we're probably quadrupling the amount of data every year. You probably know that Google data centers are all looking for places where the power is available because each data center is consuming about 10 megawatt of power. Now, you can see that every year you're going to have twice or 4 times data, and the performance per power is kind of stuck at this point. So then we're now looking into applying nanotechnology to basically make a very, very power efficient data center with high-speed computing and so on with the miniature scale so that we can start to look into miniaturizing the data center on a chip. And then you can put this chip or Lego chip and build a bigger cluster data center. And some of these data center chips can be a mobile platform so that you can have it on a tablet, and then you can have wireless and optical communications. And then a doctor can just basically carry that type of data center on a tablet or PDA into an ambulance and then achieve connectivity across the campus. Okay, that concludes my talk. Thank you very much.